Okay. Okay. In the name of God, and hello to all dear thank you for your absence in this class. We must define compact topological space or compact set in topological space. Okay, we have this definition: let X and tau be a topological space and S be a subset of X. An open cover such as O of S is a collection of open sets that contain S. In symbol, we have S is a subset of this union, the union of all elements of O. Okay, so that let me add a new slide or some new slide, and then start. Okay, I see that let X and tau be a topological space and S be a subset of X. A subset, a family of subsets of X such as this, okay, that we can denote this by O, for example, is an open cover for S if and only if at the first this family must be in our topology. All of this must be open and S is a subset of this union, the union of this family. Okay, so that we must have two properties: all of these sets must be open, or all of these must be belong to tau, and also this union must be contain S, or S must be a subset of this union. For this, we say that this is a cover. This family is a cover. Okay, because if we consider, for example, this as our set, okay, or set X, and suppose that this is our subset of X such as S, then we say that this set is a cover for S whenever the union of these sets contain S. This is our sets such as A alpha, okay? The union of this must be cover S or contain S. And we say this is open cover whenever all of these sets are open. All of these are open. We can denote this by this index family or this O, for example, okay? So that an open cover such as O of S is a collection of open sets that contain S, or S is a subset of the union of elements of this family. Next, we can define the definition of compact sets. Let X and tau be a topological space and S be a subset of X. The set S is compact in X and tau when every open cover has a finite subcover. That is, for any collection O that cover S, there exists a finite number of this open cover such that S is a subset of this finite union, not whole of family, okay? For any open collection, so that all of these must be open. Every open cover has a finite subcover. We call this as a subcover, okay? Or we can write this S is compact if and only if we have this property. If alpha is an open cover for S, then there exists a finite element of this family such that cover this S. Or equivalently, if alpha or in our topology and S is a subset of this union, then a finite number of these elements cover S2. Okay, because this is the definition of open cover. Alpha must be open, all of this alpha, and S must be a subset of this union. If we have these two properties, then a finite number of this element cover S or contain S. Okay, and this is the definition of compact. Okay, compact set. And this is very important. Okay, S is compact if and only if each open cover for S have its finite subcover. Okay, finite subcover. This is called a subcover of this cover. Okay, let X and 2 be a topological space, and fact in this topology when every open cover has a finite subcover. That is, for any open collection such as O that cover S, there exists a finite number of this open cover such that S is a subset of this finite union. Okay, we have some useful and easy proposition such as this: let X and 2A be a compact space, and X and 2 be a topological space, and f from X to Y be a continuous function. Then f of X is compact. Okay, f of X is compact. So that we can say continuous functions image compact set to compact set. Okay, if f from X to Y is f be continuous, and this set is compact, and for example this is f of X, the image of X. Okay, if this set is compact, its image is compact too. Is compact too. And its proof is very easy, because for compactness of this set, dear students, do you have my voice and do you see the image? Do you have my voice and do you see? Okay, thank you Ali Akbar and Abdul Jabbar, Abdul Karim, thank you very much. Thank you Amir, Mustafa, thank you very much. Hamid, Abdul Amir, okay, thank you very much. For compactness of this set, we must prove that any open cover for this set have a finite subcover. Okay, but by proposition 2.20 we know that The inverse image of any open set is open because f is continuous, okay? The inverse image of any open set is open. So that if we consider, for example, an open cover such as this, let this of course as a subset of 2y, okay, because we have two topological space x and 2 1 and y and 2 2 or 2y, okay. We can write as book T2. This is a topology on y, okay, because f of x is a subset of y, is an open cover for f of x. Then f of x is a subset of this union by the definition of open cover and this implies that f minus of f of x is a subset of f minus of this union, okay. We take f minus from two sided of this inclusion, okay. F minus of this is a subset f minus of this, and so that x is a subset of this union f minus of a alpha belong to I, because we know that f minus of this union equal to the union of this inverse image, okay, and x is a subset of this for all f. X is a subset of this, okay. Now by this proposition we know that all of these are open, all of these sets are open so that by, or we can say by proposition 2.20 these sets or this family is an open cover for x instead of f of x, okay, and so that there exists some finite number of these such that finite number of this open set cover x, or x is a subset of this union. For example, if alpha I equal to 1 to n, because x is compact, okay? Because x is compact. X is compact. X is compact. So that we have this finite collection. And also we can take, sorry, this is f minus, okay? F minus, and this is a alpha, not alpha, a alpha I, okay? Now if we take f from two sides of this enclosure, we see that f of x is a subset of this union f of f minus a alpha I, or f of x is a subset, because all of this is a subset of a alpha I. This union alpha I from 1 to n. So that for any open cover of f of x, okay, we find a finite subcover for this open cover. This shows that this set is compact, okay? So that for any open cover for f of x, we can return this open cover to x. All of this must be open to. All of this set must be open in x. And since x is compact, a finite number of these open set must be covered x, and so that we can take f from two sides of this inclusion, and so that f of x is a subset of this finite union. Now let's pay attention again. Let O be an open cover for f of x. By proposition 2.20, we know that all this set is open to. Since x is compact, there is a finite subcover for this open cover for x, such as this, u1, u2 up to the un, okay? So that x must be a subset of this finite union. It follows that f of x is a subset of u1, u2, un. So that this arbitrary open cover have a finite open cover. And this is very important, that any compact set image to a compact set by continuous function. It is important, it is continuous, okay? And we use this property for this, that if alpha is open, this is open in x, so that we found by this process an open cover for X, an open cover for X. Okay, and we have this easy proposition 2. Let X and 2 be a compact topological space and Y be a closed subset. Then Y is compact too. Okay? If X is compact, any closed subset of X is compact too. Proposition. If X and 2 is compact, topological space, and Y as a subset of X is closed, then Y is compact too. The proof is easy because for example, let this is Y and this is whole of X, or then proof followed by this method that if we consider a open cover for Y, because we want proof that Y is compact, okay? We want proof that Y is compact, so that we must consider an open cover such as this, okay? An open cover for Y, and we must find a finite subcover for this open cover, okay? But we note that if we added this set is X minus Y, the complement of Y, and this complement is an open set because Y assumed is closed, so that its complement must be open. Now we see that this open set added to this open cover consists in open cover for rule of X, but X is compact, so that a finite number of this must be covered X, so that we found a finite subcover for Y, so that we can write its proof by this method. Proof. This is an open, be an open cover for y. We want to prove that y is compact, so that we must prove any open cover for y have a finite subcover. Okay, so y is a subset of this union, and all of this is open, and all of these are open, or this family is a subset of two. Okay, now if we add, now we see that we have x equal to the union of y and the complement of y, and y is a subset of this union, so that this is a subset of the union of this A alpha. Okay, union by this set, and of course this is a subset of x, because all of these are subset of x, so that we see that x is a subset of this. We don't need to this. I write for you. We don't need for our proof. So that this collection A alpha union by this complement of y is an open cover for rule of x, because this union contains x, and all of these are open because A alpha is open for each alpha, and this set is open because y is closed. So that this is an open cover, but x assumes that x is open, but x is compact, and so there are a finite number of these that cover x. There exists a finite number of this open cover that cover rule of x, so that a finite number of these must be cover y. So a finite number of this open cover must cover X, and so a finite number of this open cover must cover Y. Okay, because we have two cases for the n centrifuge. This finite number of this open, we consider this open we can consider two cases. Okay, case 1, for example, this open cover selected by this element so that we can consider the case 1 as this. There exists alpha 1 alpha n in I such that X is a subset of this union. Okay, this finite cover not contain this element. In this case, since Y is a subset of X, we see that Y is a subset of this too. Okay, but in case 2, if we consider for example A1 AM in I such that X is subset of A alpha 1 A alpha M and union by this element, okay, of our cover, then we see that if we intersect two sides of this by Y, الو سلام، چطور خوبی؟ من سر کلاسم شب گفتم میخواستم بیام اونجا، نگاه گفته بود زنگ بزن، یادم رفت بگم مامنا خونم که. آره بگو حالا ما میاییم، میخواستم شام بگم، اگه شام درست کرده بود که هیچی، اگه نه هیچ. یادم رفت زودتر بهش بگم. حالا من میام پس. جان پس بیادم شب دیگه بیام، پس بیادش شب دیگه میترسم الان دوباره اینو با هم کنتاک کنم. باشه من بسه شب دیگه من هیچی بهش نگم. باشه کاری نداری؟ قربان خدا. Sorry, in this case we see that if we we see that this intersection is a subset of A alpha 1 intersect by Y union by A alpha n intersect by y. And finally this set intersect by y, that this is empty set. Okay, this is empty set. This is empty set. So that we have only this n or m set. We write m so that this is m and this is m. Okay, but this is equal to y, and all of these. So for example, this set is a subset of A alpha 1, and finally this is a subset of A alpha m. And this case again we have a finite subcover for this open cover, so that y, so that any open cover for y, any open cover for y have a finite subcover, such as this or this. Okay, let X and 2 be compact topological space and Y be a closed subset of Y, then Y is a compact set. And this is proof. And we have the Heine-Borel theorem: a subset of Euclidean space Rn is compact if and only if it is closed and bounded. This is very important, and you don't see its proof, but it is very, very important. If Rn considered by Euclidean topology, then we have this property. E as a subset of Rn is compact if and only if E is bounded and closed, and E is closed. Okay, a subset of E with Euclidean topology is compact if and only if it is closed and bounded. So that, for example, in R, in case n equal to 1, okay, this set is not compact because is not closed. Okay, this is not closed, so that this is not compact. Or this set is not compact because it is not bonded. Okay, not bonded. But for example 0, 1 is compact because it is closed and bonded. Closed and bonded. Bonded, okay? Closed and bonded. Or so that we have, this is Heine-Borel theorem. This is very, very important. A subset of Rn is compact if and only if E is bonded and E is closed. Both of these. Both of these. Or and another example, Z integer number is not compact. Because Z is not bonded. We know that this is an unbonded set. Okay? Z is closed, but it is not bonded. And any finite set such as this is compact. Any finite set, because it is closed and compact. Closed and bonded, sorry, closed and bonded. Bonded. Okay? Or in other dimensions, for example, in n equal to we see that, for example, this set of 2 such that for example x created or equal y is unbounded so that It is not compact. This is the set. If this is the line x equal to y, we consider this set as E, okay? This set, okay? This is unbounded, so that this is not compact, and this is compact set. For example, 0, 1 multiplied by 4 and 6 is compact because this set is closed and bounded, okay? And each in other dimension, we consider, for example, n closed bounded interval and form a compact subset, okay? For example, 0, 1 multiplied by 0, 1 multiplied by 0, 1 is a compact subset of R3 in space, okay? And this is the Heine-Borel theorem. And we have this important definition: a topological space X and tau is locally compact, not compact, locally compact when for each X in X there exists an open set such as U with X belong to U and the closure of U is compact, okay? There exists an open set such that contain X and the closure of U is compact. For example, Euclidean topology always is locally compact, okay? Sorry. Definition. X and 2 is locally compact if and only if for each X in X there exists an open set such that we have two properties: X belongs to U and U bar is a compact subset of X, okay? And as an example, Rn with Euclidean topology is locally compact and its proof is easy because for any x equal to x1 xn to Rn, because we consider this x as Rn, we see that this element belong to this open subset of Rn, this multiplied by xn minus 1 xn plus 1. Okay, this or u, this is an open set. Okay, x belong to u, and we know that u bar equal to this compact subset of Rn by Heine-Borel theorem. Because this is a closed and bounded subset of Rn's, so that this set is compact by Heine-Borel theorem. Okay, for example, in the case n equal 1, we see this in the line that this is a real line and this is our point. I consider this interval, okay, x minus 1 x plus 1. This u is open and its closure is this. Okay, this is u bar, the closure of u or u bar, and we know that u bar is compact because it is closed and bounded. And in other dimensions we can consider similar method. For example, we can consider, okay, for each point such as this, okay, x1 x2, we can consider, for example, this interval xx plus 1 and xx minus 1, and also this x2 minus 1, x2 plus 1, so that we have these two, and then we see that we have this open subset of R2. Okay, this is x1 minus 1, x1 plus 1 multiplied by x2 minus 1, x2 minus 1, x2 plus 1, and x6 and x2 is an element of this, because this is in this situation, this is this point. Okay, and the closure of this, if we consider this as u bar is this set. Okay, this set including its boundary, and this is a closed subset of R2 because it is bounded and closed. And in other dimension we have this proof for that Rn with Euclidean topology is locally compact space. I repeat the definition of locally compact topological space. Let X and tau be a topological space. This space is called locally compact if and only if we have this property: for each X there exists an open set such that X belongs to U and the closure of U is compact. Okay, and we have this easy proposition: let X and tau be a topological space if K1, K2 and Kn are a finite family of compact sets. Then this union, its union of this compact set is compact too. And this proof is easy. Let O be an open cover for this set. Since I is a subset of this, we have this open cover is an open cover for Ki. Okay, this is very easy because this is an open cover for this union, so that this union I from 1 to n must be a subset of this union of all elements in O. Okay, but Ki is a subset of this, so that this open cover is an open cover for Ki too. Okay, but Ki is compact. Since each Ki is compact, there is a finite subcover of this for Ki. We denote each subcover by OI, so that there exists a subcover, finite subcover, such that Ki is a subset of the union of u belong to OI. This is finite number of O. So that the union of Ki is a subset of the union of this set, but all of this is finite. Because a finite union of collection of finite set is finite. Any finite collection of finite sets is finite. So that all the union of this OI is finite. Okay. This union is a subset I from 1 to n. Is a subset of this union. OI, sorry, U belong to this union. OI, I from 1 to n. And this collection is finite, so that we found a sub cover of this arbitrary open cover for this set. So that any open cover for this set have a finite subcover, and this set, this union is compact too. Any finite union of compact set is compact. Okay, I think it is enough for this session. We can continue in the next session. Do you have any question, dear students? Do you have any questions? Thank you very much. Thank you for your attention, and goodbye. Thank you very much.